in our last video, we started proving expressions that were valid for all natural numbers. Now we're gonna do a few examples. The first one is that the sum from k equals 1 to n of 1 over k times k plus 1. I want to prove that this sum is equal to n divided by n plus 1. So let's first remember a bit about the induction. So we had a set h that we knew was a subset of the natural numbers, because the set h would be the set of all natural numbers that verify this. So h is by definition a subset of natural numbers. So what we want to do is prove that h was an inductive set, and then this would give us that the natural numbers are included in h, and we have then the double inclusion, so we could conclude that the natural numbers were equal to h. And if this, what this meant was that whatever h defined, that was p of n in this case, p of n would be this expression, it would be telling us that this expression is valid for all natural numbers. So this is what the induction means, and now we can start proving this. So first we have to say that h is an inductive set. For this I have two steps. First I have the base case, that it meant, well, prove p of 1, p of the first element in your set. In this case I want to put it for the natural numbers. We'll see an example later where this set will not be exactly the natural numbers. So prove it for 1. Okay, the sum p of 1 is that the sum from k equals 1 to 1 of n divided by k times k plus 1. We want to know if this equals that other side. Let's calculate this. This is directly the sum. It's no sum because it's only one element, so it's 1 divided by 1 times 1 plus 1. So this is 1/2. And this other side, I have to write it for n equals 1. So n1 divided by n plus 1 is 1 plus 1. This equals 1/2. Okay, so these two things, they are equal. So p of 1 is true. Now we want to prove it for the inductive step. We want to see if p of n implies p of n plus 1. Let's write what is p of n plus 1. So what I want to prove, that the sum from k equals 1 to n plus 1 of 1 over k times k plus 1, I want to see that this equals n plus 1 divided by n plus 2. This is what I want to conclude. And my hypothesis, the only thing I know is that p of n is true. So let's write our hypothesis. We know that the sum from k equals 1 to n of 1 over k times k plus 1, we know, because our inductive hypothesis says so, that this equals n over n plus 1. let's go ahead and start proving this. So we start with this side of the equation not the equation. So we start with this side of the expression. This is the sum k equals 1, 2, n plus 1 of 1 divided by k times k plus 1. Well, I have a sum, so I can divide it into two sums. This is the sum from k equals 1 to n. This is a very common trick when we have to prove something for a sum or for a product. So this is the sum until n of the same, so k times k plus 1 plus the last element, and the last element is when k equals n plus 1. So this is plus. Instead of k, I'm writing n plus 1 times n plus 1 plus 1 is n plus 2. Okay, let's see how we can simplify this. Well, what do we know? Again, we always have to use our inductive hypothesis. So I know that this is true. So let's use it. I have the exact same thing here, so I'm gonna use my inductive hypothesis and say that this equals n divided by n plus 1. Okay, we have that. It's something we know, and now we have to add this other part. So plus n plus 1 times n plus 2. And now it's just operations. Okay, we have all we knew, we have it in our expression. Now all we have to do is operations to try and get the result we wanted. So I'm gonna use the common factor here. The common denominator will be n plus 1 times n plus 2, and up here what we're gonna get is n times n plus 2 plus 1. So let's start solving. We can do some distributives here, and we get n times n is n squared plus 2n plus 1 divided by n plus 1 times n plus 2. Now this thing we have here, this is just n plus 1 squared divided by n plus 1 times n plus 2. Now n is a natural number, so in particular here we have that n is different than minus 1, always. So n plus 1 will never be 0, and we can then cancel these two elements, and what we get is exactly what we wanted. Okay, then that's exactly what we wanted to prove. So we have proven in general. We have to write a conclusion. So we proved that the sum of from k equals 1 to n of 1 divided by k times k plus 1 equals n divided by n plus 1. Let's now move on to another example. This time I will prove something similar to the one we did in the last video. It's the sum from k equals 1 to n. Instead of k, we're gonna prove it for k squared. This is a very useful expression. N equals n times n plus 1 times 2n plus 1 divided by 6. Again, let's base case. It's this expression, I'm going to call it p of n. I want to prove p of 1. Now, this side is the sum from k equals 1 to 1 of k squared. This is 1 squared, which equals 1. And the other side, this is 1 times 1 plus 1 times 2 plus 1 divided by 6. This is 2 times 3 divided by 6, which equals 6 divided by 6, so this is 1. And these two expressions, they are equal, so p of 1 is proved. Now we're gonna do the inductive step. And here what we do is we suppose p of n true. Well, what does p of n true means? It means that the sum from k equals 1 to n of k squared equals n times n plus 1 times 2n to n plus 1 divided by 6. We know this is true. And what we want to do is we want to prove it for n plus 1. So what we want to get when we finish this is that sum up to n plus 1 from starting from 1 of k squared equals, instead of n, I'm gonna do it with n plus 1, so this would be n plus 1 times n plus 1 plus 1 is n plus 2. Here I would have 2n plus 2 plus 1 is 2n plus 3 divided by 6. So I want to try and get this expression. Okay, let's start with this side. So this is the sum up to n plus 1 starting from 1 of k squared. As I said before, when we have a sum, most of the times we will divide it into two sums. This one and the last term, this would be n plus 1 squared. Okay, this is when k is up here, k is equal to n plus 1, so we are adding up k plus 1, n plus 1 squared, this one. Now again, it's always the same. This is I'm gonna write it like this. So this is my inductive hypothesis, and we know that this equals this thing we wrote in there. So this equals n times n plus 1 times 2n plus 1 divided by 6. And now we have to add this last number, so plus n plus 2 is squared. And this goes there. Okay, and now again all we have to do is operate and try to get to the result we wanted. So what I'm gonna do is multiply by 6 on both sides, so I get n plus 1 to n plus 1, common factor 6. So this is not n plus 2, this is n plus 1 divided by 6. And here we can see we have n plus 1 and n plus 1 squared. And it's important to always have in mind what we want to prove, because when we look at this, we say, okay, we want to have an n plus 1, so we don't want to cancel this with anything. We want to save this one. So what I'm going to do is I'm going to take n plus 1 as a common factor. So n plus 1, I take it out, and what I get is I'm going to distribute it here. So n times 2n plus 1 is 2n squared plus n, plus one of these is gone, and we get 6n plus 1. All this divided by 6. We continue solving n plus 1, and this is 2n squared plus 7n plus 1. Let's think about this expression. Let's look again at what we want to have. So I have the n plus 1, I have the 6. So I already have all this part. Now I need to work to focus on this. So let's do the calculations. Let's do the calculations for this. So n plus 2 times 2n plus 3. I'm gonna do all the distributives, and I get 2n squared, this one, plus 3n plus 2 times 2 is 4n, plus 2 and 3 is 6. This is 2n squared plus 7n plus 6. Okay, and I'm gonna save this. You probably already realized that this is exactly what I have here, because I did something wrong, and this is not the number 1. I didn't multiply the 6 with the 1. It is a 6, okay? So it's exactly what we have, and then we can just write what this is. This is n plus 1 times, and I'm going up again, it's that thing over there, it's this. Okay, we have this, and this equals, so n plus 2 to n plus 3, okay? n plus 2 2n plus 3 divided by 6. And this is exactly what we wanted to prove. So what we have is that p of n implies p of n plus 1. Then my set is inductive. Then I have proven it for n. So what we found is that the sum of k squared starting from 1 equals n times 1, n plus 1 to n plus 1, divided by 6. Let's do another example. So this example is a bit different than the ones we saw. and we're gonna be using what's called k-Induction. And what this is shifted induction. So we always had p of 1, we verified this, and then we proved that p of n implied p of n plus 1. And now what we're gonna do is, what if our set doesn't start with 1? What if I want to prove something for, I want to prove something for n greater than or equal to a certain number, n0, that it's also a natural number, then it's actually the same thing. So this is induction, and k-Induction is, well, prove it for your first element, so p of n0, and now do the usual, so p of n implies p of n plus 1. So the first example will be, let's say we want to prove that 2 to the n is greater than or equal to n squared. So when we look at this, we say, wait, we first have to believe this thing we want to prove. So I could say, okay, let's take n equals 3. 3 squared, this part, is 9, and 2 to the third is 8. And this does not verify. Okay, and that's why we're gonna prove this for all n natural numbers greater than 4. So the first element here is 4, which will equal our n0. So when we start with this, the base case is not gonna be p of 1, it's gonna be p of n0, which equals p of 4. So let's prove this for n equals 4. So 2 to the 4th, this is 16, and 4 squared equals also 16. Okay, so this relation verifies, and we've proven our base case. And now let's think about our inductive step. Okay, we are gonna assume, let's say we know that 2 to the n is that this relation is valid for n. Okay, now we want to prove it. Prove it for n plus 1. And the thing we want to get to, what we want to conclude, is 2 to the power n plus 1 greater or equal to n plus 1 squared. So let's start this side. We want to know what this is. So this equals 2 to the n times 2, and it's not equal. It's this, using our inductive hypothesis, we know that this is greater than or equal to n squared times 2. And now we get here and we say, well, I'm stuck. So let's think about other expressions. We know that n squared is greater than or equal to 2n plus 1. And this, I'm gonna leave it as an exercise, try and prove it. Again, it's k-induction with n equals 4. It might be valid for n equals 3, n equals 2. I suggest you try, but for now we only worry about these numbers. So that is true. Believe me, and if you don't believe me, then prove it. So what we can do is add n squared on both sides, so we get n squared plus n squared is n squared plus 2n plus 1. This is 2 times n squared. Oh, that's so wrong. This is 2 times n squared, and this is n plus 1 squared. Okay, so what we have is this side is exactly this side. So we have a chain of inequalities that proves exactly what we wanted. We have 2n plus 1 equals 2 times 2 to the n, which is greater than or equal to 2n squared, and we can use this and say is greater than or equal to n plus 1 squared, which is what we wanted to prove. Now I'm going to give you a few examples for you to continue practicing. The first problem is, again, prove by induction that the sum from k equals 1 to n of k times k plus 2 equals n times n plus 1 times 2n plus 7 divided by 6. Again, you have a sum, so I suggest you try and use the same tricks we used in the exercises. Another one that might be a bit more tricky is the sum from k equals 1 to n of minus 1 to the power k plus 1 times k squared equals minus 1 to the power n plus 1 times n plus 1 divided by 2. Now, and this is something we'll see very often. I want to talk about this. So minus 1 squared, for example, is 1. Minus 1 4 to the power 4 is 1. And if we have an odd number, minus 1 to the third is minus 1. So what this will do is it will give you 1 and minus 1s depending on if the power is even or if it's odd. And as k is moving, then we will first have k equals 1 is 1 plus 1, 2. So the first term of this sum will be positive. The following will be negative because we will have 2 plus 1 is 3. Try and solve this, and I will see you in the next video.